I'm Sonia Ye. I'm a faculty member of Transportation Technology Policy Program. Thanks for coming. I see a lot of new faces, so it's great to have you here. I'm going to introduce our speakers. And so I'll read Sam's bio. Sam has a bachelor degree, started from a degree in electrical engineering from Carnegie Mellon University. And after that, he moved on to Intel and started his own company. He still has his own company that does a lot of engineering solutions. And on top of that, Sam is also the Chief Technology Officer of Skycatch, which is a company that builds autonomous unmanned aerial vehicles, or UAVs, or drones, and offers data solutions and autonomous construction support around the world. He will tell you more about his company and the kind of work he does for Skycatch. And before I turn it over to Sam, Sam brought Brandon, and we'll have Brandon to tell us a little bit about yourself.
Thank you. I'm Brandon. I work with Sam at Skycatch and ANSYNC. I do quality assurance for drones and assemble the new prototypes.
And also, if you ask questions, Sam will repeat the question. Just to make sure that that you will be picked up by the microphone. And I will be monitoring the webcast. So anybody who wants to ask questions via webcast, please feel free to do so. And just type in your question. I will moderate the questions. And you can decide whether you want to answer a question throughout the seminar or you want to hold it at the end. Pick up clarification questions would be nice.
All right. Thank you, Sonia. I like questions, so the more and the sooner the better. That way we'll talk about what you're interested in rather than what I'm interested in. As Sonia said, I work for Skycatch, and I'm here today to talk to you about what Skycatch does in general, and really that's talking about the enterprise market for data as provided by drones or data provided by UAVs. And then just to talk in general a little bit about UAVs. So that would be maybe the first half. And the second part, we're talking about how to build a drone. And that's a fun way for all of us to look at really what they are. And I think it will allow all of you to extrapolate where they're going, frankly. So I got a quick movie to begin with. That it's a little bit marketing, or it has a little bit of a marketing flavor to it, but overall it presents a good overview of what the story is. The UCSF Medical Center. Some cheesy music that normally plays with it. Glad we don't have that turned on. So first you were seeing the construction site. Somebody selected an area that they were interested in getting imagery right away on. The drone, that information has been downloaded to a ground station, which in turn programmed the drone. The drone is now following a lawnmower pattern, frankly, back and forth. Executive brevity, it's done. It's found where its home is. In this case, doing a battery swap with some robotics built into the ground station. Shoves the battery back in. It's ready to get more imagery. So now that they have the data, this is, let's say, today's imagery. What you briefly saw was change detection, where somebody is able to say what was different from the previous time a scan was taken. They're additionally taking some volumetric measurements on, this is some pile of aggregate or material. And from the imagery, they've been able to generate a 3D model for the site. And they're overlaying CAD data. It's a little bit of a fun example here. Is the building where we thought it was, kind of stuff. That's a quick overview of what is today one of the more interesting or best business use cases. So I start off by saying that, or I intended to start off by saying that Skycatch is an enterprise data company that's collecting data through the use of UAVs. So this is as distinct from hobbyist use of UAVs and certainly military use of UAVs. And this market is differentiated by a couple of key things. One is that the drone itself is just a tool. There's some other thing that you're providing if you're on the enterprise side. And the Skycatch belief is that data is what's going to be valuable. Today, there isn't, you can't piece it together out of bits that you could buy off the shelf. If you're installing, say, network infrastructure in a new building, you can go buy bits from Cisco and Netgear and bolt them together. There isn't a way today, because it's an emerging market, that you can buy bits of solutions and glue them together. So people that are playing on the enterprise side are forced to provide the whole pipeline. That is the data gathering equipment all the way through to the tools needed to make use of it. And lastly, what separates the enterprise or business market from the hobbyist market is nobody really wants to fly the UAV. So it's another way of saying they have to be fully autonomous. That's up to and including, or most importantly, including landing. So just what we saw going on there in a schematic diagram was there was some fellow sitting at a desk who saw an overlay of the area of interest that was something like Google Maps, if you will, and was able to highlight what he wanted imagery of. That was sent to the cloud. There's a bunch of compute power available there to figure out what the flight path for this vehicle will be. It gets communicated to a computer that lives in the bottom of this ground station, which in turn sends it through a short distance RF link to the drone itself. The drone flies the mission, comes back, and once it has landed, then offloads high-resolution data. That data goes back to the cloud, where you have a lot of compute horsepower that's taking bunches of different images that are all not quite normal to the Earth's surface and building a 3D model from it. And then later on, ideally moments later, we're currently in the hours mode, but ideally moments later, other users are able to see that data and make business decisions based on it. So this is imagery from a construction site that's been pieced together from lots of smaller pictures. You can sort of see artifacts of that around the edge. This is slightly higher resolution than what you're going to get from Google Earth. And the value of this, so somebody says, well, why don't you just use Google Earth, right? We can just go get it. Well, if you go look at Google Earth, there's a building there. So the value here is the timeliness of this data. And if you're in the construction industry, you have some amount of equipment that is at play. You have labor resources that are in play, and you're up against a schedule. So you have to hit a deadline. Anything you do ahead of that is, frankly, money in your pocket from not paying for the resources. And how do you beat the schedule? You beat the schedule through better planning. So just from looking at this image, we can tell that this set of concrete is partially cured. this is today's pour. The rest of the trenches have been dug. There's rebar in most of them, but not two. So in that one image, you're able to coordinate or get high-level information for maybe 3 subcontractors that are working on your job site. A slightly higher resolution monitor, you now see the next level of detail where you can actually answer questions like, did somebody cap a particular piece of conduit in the field? So really what we're talking about is the first stage here is we're bringing resolution to the party. There's various components to this imagery that are going to yield value to the customer. At this stage, it's about resolution, that you can quickly answer interesting questions about, in this case, a construction site. Otherwise require somebody walking around who had both the level of diligence to find whatever it is you're looking for and the expertise to recognize what it was when they didn't find it. So key message there is with a low-flying anything, in this case an autonomous vehicle, but a low-flying drone, you can get the first value you get is higher resolution. So the next thing you're going to get is the ability to do measurement. So over here on the right, you're seeing somebody measuring piles of raw material that they have on site. Do you have enough? Sounds very mundane, but the downside to getting the answer wrong costs you both directions. But do you have enough raw material to pour this foundation? On the other side, change detection is completing this autonomous. So the whole data pipe, ideally, is completely automated, up to doing some level of analysis. So you could register a trigger on portions of a 2D area and say, I'm interested in knowing when something happens to my material. I'm a subcontractor on this site, and it's important to me to know if my equipment disappears or something like that. So here we're adding analytical capability to the imagery. Next step is we're going to overlay. There's various ways of doing overlay. You saw that initially with a 3D model. Here is a 2D information overlaid on 2D map data. And this is, if you will, if you've been on a job site, you still see people with large blueprints. That's why construction supervisors drive trucks. Not because they need the truck, but because they need the hood space to unwrap their blueprints. Right? They're all paper. So this is the next level where you can see the blueprint and you can see the imagery. Am I building the right thing? It's a train station, similar type overlay. This is a repeat of what I was talking before. You can do, we're only seeing in 2D here, but it has reconstructed volumetric data, so you can ask it questions. You don't need to send the guy out with a tape measure. This is a still from the same video, but now we're bringing 3D to the party. There again, it's the collection of imagery and lots of processing power gets you this point cloud. You can overlay it on a CAD model, and it gives you your first, you can immediately get insight. Am I building, as I said before, am I building the right thing? So in this case, this shows up in the point cloud, but wasn't in the model. So, somebody put some girders in there that weren't intended to be the model. Maybe that's a great thing. This is now better earthquake proof or whatever, unless there was a door intended to be there. And the whole idea, we're talking about a value proposition to in this case, the construction industry. In the first case, I was talking about coordination and logistics. Here, you're going to get an early warning if something has gone wrong. At this stage, it's inexpensive to fix. When they put a wall covering over it, it's going to be a lot more expensive to fix. probably end up moving the door. So now we switch to another market. So in the UAV-based imagery as an industry is very much in its infancy, or anything enterprise-related for UAVs is very much in its infancy. The three markets that have really stood out from the get-go have been construction, where they truly had a dire need to coordinate a very complicated logistical problem. Agriculture is not far behind it, and mining specifically has been very, very interested. I don't have anything on mining here, but this is NDVI data, which some of your ag guys are far more astute on than I am. But this is looking at the basically a vegetative health index of a field. So we're able to see, or now anybody can see, that there's some specific problem going on here. I don't know what it is. It's soil contamination, or it's an irrigation system, the center of an irrigation system. Maybe it's not really a problem. Or it's some kind of, this could be some kind of physical equipment. That might be the beginnings of blight or crop vandalism. Who knows what it is? But you're seeing that it's not anywhere near as healthy as, or it's comparable to the road area. So this is, for this type of application, previously we're carrying something either that is the same or very similar to a standard imaging camera. This is using a multispectral camera. It's going to take images on a couple of interesting wavelengths, and in this case, normalize near-infrared emissions or reflected energy from plants, normalize them against the visible spectrum, and you're able to, with a significant amount of calibration, you're able to tease out plant health. That's where the false color image from the previous slide came from. Here's another one of the same thing. This is a test field from a winery, and they have deliberately set up plants that are having trouble for various reasons. So, like missing plants, ones that are underwatered, misapplication of fertilizer. And the idea is that you can rapidly and even in an automated fashion scan thousands of acres of farmland and pinpoint areas that are suboptimal from one reason or another. So again, this is all about specific application areas today where there's a return on the investment to implement this type of system. So our own electrical version of plants can be measured in much the same way. So this is a photocell array. I noticed you guys have a parking garage over to the other side with a bunch of solar cells on the top. Are they all working perfectly? Yes. Yeah, they're all working perfectly. So that's great. They don't. That array is very typical of these garage arrays. There's not a lot of data that comes from individual panels. After a while you aren't getting the energy you were when you first installed the thing, but you don't know whether it's because you got those very inexpensive cells from some less reputable foreign country, or is it because the birds have been spending too much time up there, or is it dust? You just don't know, right? Or are they breaking? So in this case, you can take with a thermal camera, so yet another type of sensor, you can take thermal imagery from a set of solar panels, and the ones that are warmer because they're absorbing the energy, not turning it into electricity. So in this specific case, we're able to say right away that the area 2 panels, something is wrong. I can't tell you what's wrong with them, but if you were going to go look to fix them, that's where you should go fix them. So that's just a brief run-through of the type of applications that we're looking at today. My hope is you guys come up with some very interesting usages for aerial collected imagery. the larger industry is going after all kinds of things. So, Amazon thinks that they're going to deliver packages to your house. With drones, I don't know. Maybe. There's right now, Skycatch has people in Nepal looking to do what they can to help with the rescue effort. They've been flying. It's no longer viable today, but flying thermal imaging cameras. They're certainly using them for damage assessment and recovery planning. And there's other ones that at least when I initially heard of them, it sounded crazy, but as time goes on, we'll be able to make the case for them. So, bird dissuasion. Who would have thought, right? Turns out, if you're in the business of producing clean energy, wind farm is a great way to go. And everybody except the people that live under the wind farm are really happy to install a wind farm, right? Those guys are unhappy. There's nothing to be done about them. But everybody else thinks wind power is great. Until you start killing off a couple of birds. And then, some more people get upset. But it was a sparrow, or it was a robin, or a pigeon. And granted, it was regrettable they got killed. But if you're the manager of a wind farm, your bad day is not much wind. That's a bad day. A bearing failure is a really bad day. But your worst possible day is you go kill a bald eagle, and that's happened. So initially, when people talk to me like, "This is ridiculous. We're not going to chase away birds with a drone," but when they laid out the use case for them, it was very compelling that it would allow them to operate a wind farm where they were otherwise at risk of killing the national bird. And so as time goes on and the technology gets more mature, it's going to find its way into more and more markets. And I think you guys are going to think of something cool. So the next set of slides are around how I'm going to make you all experts in building a UAV. Does anybody have any questions about these ones? Or any use cases? So emergency response, in my mind, comes in a couple different forms. The first form is in finding people. So if you are trapped without water, you have somewhere between hours and some number of days for somebody to find you. Otherwise, it's game over. And as long as you're emitting a heat signature and close enough to where it's visible with the right kind of equipment, this could potentially give an advantage of finding you. The next stage is, people talk about bringing in emergency supplies. You are stuck somewhere, and I'm going to get you something that you need to survive. It's one of those things that sounds good. It's hard to see exactly how it would play out. But finding people is the application I had in mind. So that's a great segue into the rest of the slides, but you very much want to use a vehicle model when you're thinking about this. Oh, sorry. The question was, thank you very much. The question was, how much weight can these things transport? And my answer is you should use a vehicle model intellectually, and a small vehicle can't carry very much. A big one can carry a lot more. The scaling, though, is not as good. Right? So something like this, we can do, 2 to 3 pounds. It cuts into our flight time. You can build something with think of like under 6 feet that will, for a short period of time, lift 50 to 60 pounds. These are like record-setting configurations, and that's not for very long. I don't want to make any mistake about it. It's not an efficient way to move stuff, unless it's really hard to get to any other way. So that plays into the the Amazon model. I really hope they're successful, but the first market for Amazon is going to be Rapunzel. There's no other way to get to her other than a drone. Yes, that'll work, right? Yeah. So that is a market we're looking at. you can buy today ones that are half the size of your hand that send back real-time video. So that's, I don't see it getting much smaller than that. But hand size is very viable. Sir?
So the construction industry for the last 10 years has been using ground station 3D high-resolution imagery for millimeters.
Yes.
Differences and all that. Why should you go to this?
So I would say for, I guess I would, the easy answer is no. Oh, so the question was, the questioner says, I'm in the construction industry. I have some equipment that will do millimeter accuracy from ground-based platforms using some like LiDAR type scenario, so a laser-based system. Why do I want this? And my answer to you is, you probably want what you've got. It's working well for a very high resolution, close range. The advantage of this is going to be with a fully automated solution, you don't need the operator. So your particular task is something that's tied to an expert operator that is operating the machinery, collecting the data, and then figuring out a way to disseminate it within the company. So first step is you're not going to need an operator. And the second step is just the scalability of it. That if you need a much larger area and you want it collected every day, this is going to be a viable solution. And I would suggest that that probably isn't going to be a viable solution. But fundamentally, I would say what you're doing, this is not going to replace what you're doing. It's a separate set of information that's going to probably be used for a separate set of decision making. But I have no personal experience operating the equipment you're talking about, so I don't want to.
Follow-up question we can talk about.
Yeah.
How does a fully automated
Oh, great questions.
avoid birds itself?
Okay, so this is a great question. So the question is, I'm talking about scaring birds away. How does this avoid birds itself? So the answer is, we don't have a solution right now for avoiding birds, but they're more than happy to stay away from it. Depending, and this gets interesting. This is stuff I had no idea before I started this game. Depends on the species of bird, how they behave with respect to it. So little birds, they run the hell away. Right? This is something that's probably going to eat them. Birds of prey, however, are used to being the top of the food chain. There's nothing that goes after them except swarms of little birds. So in doing the tests for this, we had to create a swarm of UAVs that was compelling enough to these top of food chain birds for them to run away. But that wasn't really a question, but we have not had an incident where a bird has come close enough to be at risk. But in the specific case where we're trying to chase them away, we're using sets of cameras to figure out where these birds are to chase them. And it really is chasing them. I mean, just another example of bird dissuasion. Was it Scully? I've forgotten the fellow's name that ditched a Boeing 747 in the Hudson River. I mean, that was, frank. It was really nice that everybody survived. That was birds.
I don't think that was.
Oh,
But anyway,
okay.
It was pretty amazing.
Somebody made an unplanned landing of an airplane in a river on account of the activity of birds. I was just using this example. And then there's other examples. I had somebody come to me, talk to me about, while we're on the topic of other examples, young deer, Bambis, in a field. And this is a hay field near, and so in European countries, I guess that's less like the way the U.S. is set up with huge, whole Midwest. Yeah, they have smaller fields surrounded by, at least as described to me, surrounded by woods and whatnot, and they end up with young deer in the field. And then the field has grass cutting equipment. Explained to me, I said, well, why don't the deer just run away? This is not a use case. This doesn't make any sense. As was described to me, the deer have evolved with the programming, the baby deer, that when there's danger nearby, they just huddle down and they don't matter what. And then you've got the grass cutting equipment coming. It makes a huge mess, and it's really bad for the deer especially. And they're the way the government is set up, and with regard to fines and whatnot, it turns out there's a compelling reason for them to figure out where these things are and avoid them with the cutting equipment. Again, I'm just using this as an example of the type of applications that are showing up. Not something we're going after right now, but I think this is going to continue. Smart folks are going to find interesting ways to make use of this technology, especially the data. Sir? No. Yeah, that's not really my department. I'm on the engineering side. But I can put you in touch with somebody who's happy to sell you a system. Sir? Yeah. So the question was, how far apart are the technology involved in the military UAVs or drones from the civilian ones? So I'd say at the outset, there's three distinct markets. There's the military market. They're interested in killing people, right? Sure, very effective. The hobbyists are interested in flying them, and hopefully not killing people. It tends towards a very different implementation. It's just not the same. And you could look at the aviation industry as a parallel. Right? Yes, they're using the same jet engines, but the thing that your fighter plane and a passenger plane end up being a very different vehicle. So how far apart are they? I think the gap is closing. I think that in some respects we're ahead, we being the enterprise market, in terms of how seamless the whole thing is connected together. They're able to throw bodies at it. I get the data from this guy, send it to this guy, this other guy processes it with this tool, and so on and so forth. So making it useful, the whole pipeline, as it were, I think we're ahead. They're certainly leading in terms of longevity. They can do like hours of flight time and things like that. In terms of cost for the mission, there's just no comparison, right? You're not getting into a military UAV for south of $1 million. It's just, sir. Yeah. Yeah. Right. If you're talking about Skycat, so the question was, I'm being obligated to repeat the questions, just so you know why I'm behaving in this perverse way. I think the question was whether it was directed to me or Skycatch. Is the involvement focused more around the drone itself or the rest of the infrastructure, and if so, where? Is that no? That was not the question.
The question then comes here is, so I'm very much in the classification business of remote sensing data, but I was just wondering, and there's a lot of complications and challenges in data spectral repeatability and calibration of your data. But I was wondering if you could tell a little bit about what sort of, in the hardware side of the drones themselves, what are the biggest challenges, and what would we expect to be sort of the next generation? What's going to be so much better in a couple of years, just in terms of what you put on the table there?
Okay.
That would be the question.
So you said you're into the analysis of the data.
So I collect a lot of hyperspectral data, but I'm more like in
Are you by chance looking for a job? We have. I saw it. Just jump in there. Skycatch is growing like anything. We have job openings. All right. So what are the next steps? we're, as far as Skycatch is concerned, okay. So the next big jump, and this is where Skycatch is focused, is not glamorous. The next big jump is that the plumbing is perfect. Right? So we don't say that, but it's more than just crashing, right? It's that it comes back to where it's supposed to be. We're the leader in that. Our results are very good. But beyond that, the data is pulled out of the camera system on the UAV. It's uploaded to the cloud automatically. There's not somebody that needs to be involved. All that data, which is, in the case of a standard mission for us, 400 images, is all glued together correctly. All the useless data is thrown out. You get a nice, clean data set. You get an email in your inbox. It says, Sonia likes your picture of something or other, and then you have something else from Facebook, and then you have a similar type thing from your cloud-based data management tool that says, you have another scan waiting for you. You click on the link, it takes you to your area of interest, and everything is there for you. It's done the data pre-processing that you had asked it to do, and it's immediately useful. That, I think, is the next big jump, that the whole plumbing. Yeah, that's what we do today. It all gets uploaded to the cloud, and then we have a bunch of servers that are chewing on this data to, as quickly as possible, get you that one clean data set. Oh, so I think the question is, uh-huh. Okay. All right. So I'll say, if you'll allow me, I'll summarize your question as, what about adaptive flight path or adaptive flight planning? At the moment, it's all pre-programmed. Pre-programmed, so from the time it leaves the base station, it's not going to change its flight pattern unless it encounters adverse conditions. So things like battery level is lower than expected, wind is lower than expected, it receives a signal that there's a storm coming in, things like that. Then it heads back home. But the compute power is available, the infrastructure is available. If there was a business case for it, there's no reason why I couldn't do it. We have plenty of compute power on the drone. There's a radio link that's for telemetry and on continuous communication. That could be done. Sir? Oh, I've been told you're allowed 2 more questions, and then we'll burn through the rest. Sir?
Where a nation's scheduling about 20% savings in that water, 80% of water times 20%, that's 16%. That's more than all of our cities. When you start looking at the kind of conservation we can get, it looks really good. And we passed the water bond, and I don't think there's a water project that could come close to just putting up a lot of UASs and trying to get that water conservation. Have you guys been looking at that? And would you get that with the suborbital UAS, or would you do it with maybe a series of the kind of products you have, or it would go from place to place and gather multiple spectral?
So we have a fixed-wing glider, autonomous glider, is what you could think of it as, that we're using for ag applications. So a lot longer flight time, you need a lot more imagery, and it's not practical in half-hour flights. Okay, at the moment, so we have a program for a high altitude glider. This is at 60,000 feet. That's a whole different endeavor, and we made significant progress in that regard. We've taken imagery at that altitude. At the moment, the deployed solutions are this, a quadcopter, and a low altitude glider. So, all right. So here's the thing. Keep thinking about these cool use cases. You guys have specific domain expertise. You're the ones that's going to come up with some cool data and some cool way of processing it using some interesting sensor that can take advantage of this technology. All right, so how much time do we have left? Is this a 40 minutes? Great. Okay, that should be more than enough time to make everybody an expert in how to design these drones. And feel free to ask questions as we go along. So I'm going to say, so what do we have to figure out to make this drone? We have to figure out a propulsion system. How we're going to get it off the ground. We have to figure out mechanically how we're going to hold all the bits together. And we have to figure out a control system. How we're going to keep it, how we're going to make it fly to where we want it to go. And I would argue, this is where we're doing our specification. And I think, we have lots of vehicle experts here, I'm told. I think these are the only 3 questions you really need to ask. Anybody got any, to design any vehicle? No argument? See? They all agree. Paint color, right? Or whether it has a CD player. So payload, what are we going to carry? And this comes down to, there was questions about sensors, right? Or what's the next thing? We talked about multispectral cameras. We talked about thermal imagers. We talked about visual spectrum cameras. Some of them are heavier than others. Is there a scale factor? Can I do 2 things at once and achieve more value out of it? If you will, this is the carpool lane. Right? Am I going to put 2 people in my vehicle and I get a better payload out of it? How fast do I need to accelerate? So here, you need to beat the acceleration of gravity. Otherwise, you're going to stay on the ground. In a car, this is can you beat the minivan, right? Sorry. You're unhappy with your car purchase if you pull out from the red light and the lady in the minivan is way ahead of you and you can't make it to the entrance ramp. And then you guys are all energy guys. This is where we're trying to figure out how to power the thing. It really comes down to the very last portion of the trip. Where is that coming from? So your best case scenario is if you were tethered, or you had overhead wires like a tram. In our case, we got it in batteries, and we have to carry it the whole damn way. Talking about underlying technology. What are we going to use for our power plant? So people who are worried about reliability, and this would be my pitch on one of the reasons why this technology is going to continue to take off. People get excited about the invention of the jet engine having one moving part. That's kind of BS. I mean, you look at it has one moving part, but it has like 1 million parts to make a jet engine. To make this quadcopter fly, we do have 4 moving parts. We have 4 engines, and they're frankly very, very simple. It's termed a brushless DC motor. There's a stator in the middle, 3 sets of windings, and a ring with some magnets in it. We got torque curves. So based on the previous slide, what I'll say is for our UAV design, and it extends to any vehicle, we're really interested in weight. That's the most important thing. Almost every decision comes down to weight. So on these curves, we're looking at the next step back from weight in order to achieve acceleration is your torque curve. So with an electric motor, you're really good at low speeds. On a gas engine, they actually don't even bother to plot it anymore. Right? They've just given up showing what the torque might be at these lower speeds. And you can fix it to some extent with a gearbox. It's the whole purpose of the gearbox. That only does so good, and it costs you more weight. And this is the domain. Really, this is the domain where one of the two domains where the hybrid plays. It's fixing that problem. Again, we're designing our own drone here. So we're looking at the efficiency curve on one of these motors. And you're going to get this same curve out of any power plant. We're going to say in this case that we want to hit whatever we do with this motor. This I don't think is actually the motors we're using, but in this case, we want to be tuned around 2,000 RPM. Maybe missing my mark here, but I'm trying a little bit to play to the audience that in any vehicle design, you go back to this one with the gasoline engine, you're going to have an efficiency point where you want to operate that. You're going to put in a gearbox or maybe a hybrid system, try and stay there. All right, now is where it gets more interesting. So we have the weight of the vehicle. We're going to say it's about 5 pounds. I'm going to say I need 10 pounds of thrust. So for a fairly docile vertical takeoff and landing vehicle, you can say that you want twice your weight in thrust. You're going to burn half of that to keep it afloat, if you will, and the other half is going to allow for maneuverability. Once you have that number, you're going to pick a prop, a propeller, that when you divide it by, in this case, 4, roughly, is going to give you that thrust. You're going to have a number of different options, and you're going to pick one that gives you the greatest efficiency for that thrust. You're going to be limited in the size, because you have a guesstimate of how big your vehicle is going to be. You're going to pick your prop next. Once you got that prop, you're going to do the same thing with the motor. To achieve that level of thrust, a set of tables that are produced from a simulation, fluid dynamic simulation of the prop, you're going to have an RPM, a speed that motor has to turn at with a given torque. And lastly, what you're going to get out of the back end of this is you're going to end up with your travel time. You know what battery you had based on your weight. You know what power that this motor took to achieve the torque at that RPM, which in turn produced the thrust you wanted. You're going to be able to it's going to take division, and you'll be able to get your flight time. And this is where the loop goes back. You say, that is not sufficient flight time. And then you're going to look at going for the bigger battery and more weight and how that's going to affect your optimization. Somebody who's very savvy with solving complex systems could potentially build a solver for this. The model for the props are generally table-based, so it does make it a little bit. So so the question was, what's the average size of battery? And that's all. It all comes down to weight. So whatever your payload is. So this is, I think this is about, this is a 2-pound battery, or fairly close to 2 pounds, this one. But this is a bigger than this by the way is our prototype of our next generation. This was finished yesterday. There's 2 of these in existence. The other is in Japan. We're now moving up the ladder in terms of battery capacity. This is, was it 6,000 milliamp hours of capacity. So the question is, what's the average speed of drone? That's going to vary. Again, we artificially limit the speed. This one can go without without being speed limited. This one can go 60 miles an hour. So we've done exercise where we chase it in a car and things like that. It's very entertaining. So if everything goes well, afterwards Brandon will take this on a quick test flight out front for anybody that's not headed over to Froggies. So won't go into this too detail, but this is again back to energy and weight and how it all relates to flight time. And this is the same as any of your vehicle problems. This is our conversion of weight to distance. So we got energy density is not what you're interested in a flying vehicle, which was power per volume. It's fine if it's a bit bigger. We're interested in power per weight, specific energy. Gas is something like 40 times better specific energy, which everybody would say we just give up. However, the motor that we have is much more efficient than the internal combustion engine. And then we get this interesting credit in terms of the power to weight. It's the opposite. We have better power to weight on an electric engine than you have on a gas engine. And it favors adding more and more batteries because you can make up for it with only a slightly more powerful engine. And that's if you want to go back to the vehicle analogy, that's what happened with Tesla, right? They built a Roadster. They could get a certain distance, and their view was, I don't know this firsthand, but it mirrors the data. Their view was that they needed longer range, and the way to do it was they came back around to bigger batteries and bigger batteries, but their motor only got slightly bigger, and so it worked out. And that's why they currently manufacture the heaviest sedan around. That's where the numbers pan out. And we have, to a point, a similar thing with the UAVs. They're going to get bigger for the flight time. And that relates somewhat to the efficiency of, there's another line in here of the air interface. The motor air interface is the prop. Okay, so we've done our high level, right? In these last couple of slides, we've figured out, we had to decide up front what kind of camera we were carrying. We're not carrying bombs. We're carrying probably some kind of camera. And then we've had to have to size the rest of the power plant. I'll just give one slide here related to construction technique. Back to the my original theme, it's all about weight. You see the vehicle industry is moving from mild steel to now aluminum. Aluminum is similar strength to weight, but they can put it structurally. They have more freedom to generate the strength that they need. Carbon fiber composite gets you both. You can form it into structures where you get the strength you need. You're not wasting extra material where it doesn't need to be. And it does have better strength to weight. This is a machine that we have up in El Dorado Hills where we worked out a way to make these type of composites quickly. So this is a compression molded composite. It's rather than hand layup, which our previous generation were. It's very expensive. It's limited to Formula One cars, frankly, and some high-end BMWs. This one you have, it's almost like an amalgamation of fiber and resin, and with a 200-ton press, we're able to squash it in a pair of molds into the shapes you see here. This is our raw example of it. So, when all of you go to build your drone, I'm encouraging you, step one, to address from the beginning and at every stage the weight. Work out a construction technique that's going to continue to minimize your weight. And I think this goes back to vehicles as well. This is mass that you have to accelerate from every stop sign. There should be more focus on reducing the weight of the vehicles than maybe it's currently played out. Other aspects to the drone design. Here we have, and this plays into your question about what's next. The lower section of this drone is configurable. The whole blue bucket can swap out for different sensors. So if you have a very specific application, you need a very specific filter on your multispectral camera. A payload can be developed and swapped into the power plant of a vehicle without a tremendous amount of engineering effort. Okay, have I got everybody? We're going to now design the control part. So this is the really cool part of what makes this possible. This is only very recent that people have worked this out. This is a quiz. We have a mid-talk quiz. Are we on a time? Mid-talk quiz. So you have some flying thing. Somebody told me Froggies was the place to. What's Froggies? Is there something called Froggies? Nobody knows what it is. Okay. It's a burger place. Our drone wants to get to the burger place. And at the high level, we've figured out which way it is to get there. So we need to gain some altitude because we don't want to hit people on the way there. And it's, due north. So what's our red line? Why did we add this other vector there? Anybody got a guess? Well, this was our green. We're calculating a thrust vector that we need in order to get to Froggies. So we know we need to go up. That's our green. We need to gain some altitude. And then we've got to go north. I'll let you off. It was probably in the presentation of the question. The red component is gravity. When we're doing this math, we always need to add in a significant vector to our math to account for our buoyancy, if you will. So we do like your Physics 101 vector addition, and this tells us what attitude the craft needs to be. Start heading there. Okay, now is the trick that makes these things work. If you intellectually think these through, it's not, at least my first go at it, wasn't clear to me how we're going to get this thing to rotate. And the trick is you have two different types of props. They spin opposite ways. So the front two, and you can do either way, but the front two turn inwards. So they turn in on each other. And you have multiple ways of achieving lift. So I can balance the thing in air with 90% of my power going to this pair and 5% going to this other pair. I'll stay level, but the net effect is it creates a torque around the center axis, or the z-axis, and the craft will rotate. So just to kind of keep this in context. The first slide, we're talking about how one of these things is going to pick and move in a particular direction. And it's as simple as it looks. If I want to go this way, I'm going to create more thrust on the back ones. If I want to go this way, I'm going to more thrust on these two props, and similarly. The interesting part is, how do I turn to face a given orientation? So that's this, making use of the alternate ways to generate similar thing the opposite way. I get into the core of the flight controller algorithm. This is running at about 200 hertz. So 200 times a second, there's electronics that look like this, that are inside the UAV, that are figuring out primarily how to keep the thing stable, but as a secondary operation, how to get to where you want it to go. So there's 3 control loops within each other. The outermost control loop is we're saying that we're half a mile from our destination, and it's this particular heading. What we talked about in the first slide was lean angle. So we're saying that we want to get there moderately aggressively, so we're going to do a 15-degree lean angle. And the last stage, you're looking at the inner control loop is controlling that lean angle through roll rate. So how fast are we moving to the desired lean angle from where we were? And that all gets, these sensors these days This is an image of the board I was holding up. There's a lot of sensors on this thing to make it work. 3-axis accelerometer, gyro, magnetometer. So the accelerometers and gyros are associated with keeping the craft level. The magnetometer allows you to know, based on GPS position, you know you're not where you want to be, but the magnetometer is going to tell you if you're heading, what heading you would need to adjust to get there. And the barometer is adding additional input to help resolve altitude. You don't get very good altitude data from GPS, and including barometer data is handy. Any other questions about how to design a drone? Are we all give enough detail? So we're one of the few companies that has our own flight controller. We regard that as key to making sure the entire system operates at the reliability level demanded by that market. So the hobbyist market has done a fantastic job of producing very inexpensive flight controllers, but they're not particularly concerned if some small percentage fly away or meet some untimely end. That's a different market. So, this is we're required to make our own. This one has other things where it includes the ESCs. So a single board here has 5 processors. This is a CPU. It's running just shy of 200 megahertz. This is the sensor I pointed out that's doing, that has the gyros and the accelerometers in it. This is a barometer, all really tiny parts these days thanks to the semiconductor industry. And then 4 ESCs. So this circuit is equivalent, and each of these is going to control one of these motors. So while the motors are mechanically very simple, it does need some brains to figure out exactly how to commutate it. But that's everything to fly a vehicle on one board, up to and including a mini or micro SD card that logs all the data. We have a separate computer that handles the imagery and high-level functions. But as far as keeping it level, this is all that's required. Sir? Oh. Yeah, so a helicopter... Oh, sorry. The question is, why don't we build a helicopter? A helicopter has to have one that seems easier and better. So, yes, helicopter is from 50 feet away, a helicopter is simpler. But from 4 feet away, if you look at I'm not sure the technical term for it, but the whole interface of the hub, the swash plate, and that coupling mechanically is very complicated. So really what we're doing is we're trading off mechanical complexity for electronics and software complexity, and this scales better. Mechanical stuff is not getting cheaper. The electronics is now very cheap to do. And a helicopter does have an efficiency advantage. Bigger prop is a better air interface. Anybody else? I'll build one. But 4 is the minimum, unless you have an articulated joint, which there is a 3-prop configuration. 4 is the minimum to allow you to preserve orientation and direction. So there's people that have actually built ones with just 2. They wing around as they're flying, and they have an amazing amount of compute power and cameras to figure out their orientation, and they can fly. So let's see where we are. End here. The only we've finished our drone build. As far as the market goes, Skycatch is betting on battery swapping. We have a charge-in-place solution now. We have both now. The bulk of the deployments are charge-in-place. Very similar to my electric car. When I bring it home, I plug it in. But we believe the high-end market is going to be for instant availability of data is going to be serviced by something that swaps a battery. And you saw that at the very beginning of the video, was a mechanical battery swap. And my plea for weight. I'm slightly bending data here. It's not a fair comparison. But for all, I'll make it me versus you. For all you're trying, we haven't improved that much. It's obviously not the same car, but anything we improved in energy efficiency, we gave up for an increased weight. This is currently our prototype battery. It has features in it that allow to be grabbed by a robot and pulled out. So the question is, what's the charge time? So yes, we can, if we're aggressively charging, we can charge in 15 minutes. But all the same rules apply as from electric vehicle. If you charge aggressively, you limit the cycle life on your batteries. So as just as a rule of thumb, a starting point, you want to kind of think of as flight time and charge time as being similar. With some of the special battery chemistries, you can charge a lot more quickly. But this is what will limit this technology to, at the moment, periodic flights. With battery swapping, we want to look at as instant data. So you have a facility, you're a large construction firm, you're putting in a liquid natural gas plant in Australia, and you've got an invoice for somebody saying that such and such has been delivered to site. You want to check? Well, you can carve out the area where it was supposed to be delivered, schedule a flight, and you would like to see in 20 minutes or less, you've got the data back. You can then go take the volumetric measurement tool, check, you say, yes, I got the aggregate, and it's this volume. Material received, pay the invoice. Certainly. I've got a microphone. I love a fight. Sure. So the suggestion was, this is sure. So the suggestion was, don't bother with battery swapping, just get more vehicles. So at home, I have a Ford Focus Electric. It's a very nice car. I recommend it. So rather than worry about charge time, I should just get more cars. I'm going to fill my whole. But you're right. So the analogy, I think, another analogy that is printers, office printers, right? So and it truly do go both ways. There's scenarios where every office has their own little, we'll say crappy inkjet printer. Everybody's got their own one, and it doesn't matter. You want to print something, you print something. And there's other offices where there's this massive Xerox machine in the middle, and everybody is sharing it. And clearly in the printer market, it must be close enough that there's not a clear winner as far as which way to scale. And the jury's still out as far as how this will scale. If we can make the robot very reliable and inexpensive, it will be the way to go. If the robot experiences reliability problems, what you're suggesting will be the right way to go, provided the sensors don't get too expensive, right? You said you're into hyperspectral imaging. How much does one of those sensors cost? Case closed. I think I just won. Anybody else? Anybody else got a question? He gets better data. He better.
Have drone go
30, yeah. And this one will be able to do high 30s.
Gather a lot of data at 60 miles an hour.
Absolutely.
So is your model that you're going to have multiple charging stations, you're going to land them, swap out, and go on to the next charging station?
So the question, I'm getting better at this now that I'm at the end. The question is, do the economics favor more ground stations or more sophisticated ground stations? And I'm gonna replay the printer argument. It depends on the market. So if you're at a small construction site where one flight a day is all you're really going to make use of. You're going to fly at the end of the day, collect imagery. Somebody's going to do planning very early in the morning and disseminate instructions for the day. We're not going to do battery swapping. It's a plenty of time to charge. In fact, we're going to specifically set that one up to charge really slowly to increase the lifetime on the batteries. If you're in a production environment, some of these construction sites are enormous. They have huge dollars at play. And the penciling right now is that a more sophisticated ground station with battery swapping will win. But it's the devil's in the details, right? So you're building a little house for it, a little wall so people don't rip it off and stuff like that. That's a cost. You have your $60,000 sensor that certainly pushes you in one direction or another. But there's going to be different markets, and we aim to provide the best solution in each market. Sir?
So going back to
Birds, yes. What about the Bambis? That was a vicious end. Go ahead.
So, on a broader sense, fail-safe sense, how does this operate in a fail-safe sense?
Okay, so the question had bunches of components to it, but I think in summary we could say, how do we operate these things safely, right? And there's hazards associated with people, other drones, and airliners. Is that a fair characterization of the question? So let's do the most problematic or the most worrisome one first is airliners. And it actually does extend into the other questions too. The way to deal with airlines is the way that airlines deal with the problem right now. It's around airspace. So we're going to stay below 400 feet, and airplanes are going to stay above 1,500 feet, except in very special circumstances, they can be down to at 500 feet, like in remote Alaska or whatnot. So that's giving you a pretty wide buffer. There isn't really a use case today for us, or we're not finding a real need to get much above 400 feet. It doesn't do us much good. We'll say categorically, we don't fly near airports. So hard-coded into the flight controller, this one doesn't have it right now, but the next generation flight controllers have, if you will, a cone of interference around airports. As you're right next to an airport, this three-dimensional cone creates a ceiling, an operating ceiling for the vehicle. You can't fly up into airspace. And it grows the further away you get. So I think the risk of airline interaction is very small. Right now they're low altitude, so they're playing by the same rules. But a high-altitude glider is limited to above 60,000 feet for the same reason, as you're getting above all air traffic. It's you and a couple of U-2s and stuff we don't know about up there. It says, can I get away with a 500-word essay instead of a 750-word essay? Is that what it said? Yeah, we got a special dispensation, 500-word essay. If I want to fly your UAV over a stretch of freeway back and forth for an hour to track traffic congestion on the road, how much does it cost? Also, would your software be able to extract vehicles' travel speed? So I don't have pricing information, and I would say at the moment that's not the type of... I would steer away from flying back and forth over cars. Just categorically, at the moment, that's not a good idea. But it's reasonable. It's something you could do. Could you track and extract all the traffic information? Yes. We don't have algorithms in place today, but you absolutely could track that. Yeah, I'm not a real expert on that. I can give you sort of the framework as I understand it, but this is wrapped in all kinds of caveats in that I'm on the engineering side, not the policy side. But the summary deal is that at least today the use of UAVs is being regulated around money, frankly. So if you're operating your drone over your land in your airspace, which is say your airspace extends up to 400 feet, you're fine. Do what you want. Now, the point where they're trying to regulate is if I pay you to operate on my land. And they're saying that is not allowed, except through exemptions. And so the FAA has an exemption process where you apply for it, and I think Skycatch has the most exemptions of anybody out there. And they're around agriculture, mining, and construction so far. They're great use cases. They're very safe. There's very few people there. Again, I'm not an expert on it. I do know that our exemptions are site-specific. But it's regulated around, like, money. So if you're not paying me, and I believe it starts to fall more under this hobbyist recreational use, which predates the FAA, frankly. So, okay, we got a correction here.
If you, for example, fly over a farm and you're doing it recreationally and you don't sell produce, no problem. The moment you sell the crops, it becomes a post facto aviation safety problem. There's a joint resolution coming out of Senator Walt's office that will be introduced next week, which would allow farmers to fly for the purpose of water conservation under FAA emergency powers. That would alleviate that for California during the drought.
Yeah.
The other thing is, if I want to do research on your farm with a UAV, I need permits as well. And I need the same permits as if I was going to fly at night.
Right, but so I shouldn't talk any more about this. It's not my area of expertise. I think if you're flying on your farm and you own it, I think you're okay. Okay. No more questions on that. Hey, sir. You have an argument. Great. Even better. Okay. So I think that it was a suggestion. Is that fair? And
So if you can, who's the one that's at interest in the huge project? It's the developer, and the developer needs insurance, and he doesn't want this guy to put in those extra parts you mentioned, so there's an insurance company behind the developer. So get the insurance company to require your data. What data do they need? So talk to the insurance defense attorneys and see what they say, and then go talk to the other side and see what they say.
All right, so I think the suggestion was fear of litigation is a great driver for a defensive maneuver in collecting lots of good data. And the questioner is imagining a scenario whereby the underwriter for the insurance policy you have to defend against litigation becomes the proponent of the business. And I don't remember the details exactly, but we did have a scenario where there was a safety incident and there was the beginnings of a complaint process. And by looking at the imagery data, we were able to say, this did not happen in the location or the time as being claimed. We don't know too much more about it, but we definitely know because we can see all this equipment is still here and it's not where you said it was. So I agree.
But me being the chair, I'm going to take the advantage and ask the last question. That's a question that Professor Michael Zhang asked that I don't think you fully answer is, you can collect 3D data, right? Can you collect the speed data? So we're doing transportation research. We're really interested in measuring the speed of traffic.
Okay, so just let me say, Peter gave me these. These are flyers. So there's those flyers related to the ASPRS up here. Have a look if you're interested in drones. I don't know anything about it other than what Peter told me. But so the question was, you said it in the microphone, so we're good. Can you collect speed data? And Sonia said that you can collect 3D data. So we would be able to do either, but not both together. So the 3D data relies on gluing together lots of imagery and of largely stationary objects, where you can find the same bits of imagery in overlapping portions of the data. For taking speed data, yes, you're going to collect. You're going to get as high up as you can, and you probably wouldn't have to move back and forth over the freeway. You can take images separated in time, otherwise known as a movie, and you're going to use some of the same algorithms that are used actually for MPEG compression, where they're finding a chunk from one frame to the next. They're finding a chunk of image that's present in both successive images and doing motion estimation, saying where does that image show up, what is the distance, the disparity between them. Those algorithms are very well established, and they could be applied to the data sets that we would gather from a drone. So the answer is yes. We don't have a solution in place today, but using existing equipment. And are we still going to fly?
Sure.
So we have, this is a prototype. It's flown once. Brandon is going to fly it manually. It's not in autonomous mode outside, just to give you make a visual connection for what these things do and how they behave, if you're willing still. Thank you all for coming.
Turn it up. Thank you.
Oh, good, yeah. Yeah, I thought it was, yeah. Yeah, it's